Now we've covered basically every single example for Sn1 mechanisms, and so we are able to do any Sn1 problem. So let's start off with this first one. In this first one, we have a secondary carbon right here with bromine, and it has a tertiary neighbor. And so we notice that if we have through this Sn1 mechanism, because we know we have silver nitrate, bromine will leave on its own, we're going to get a secondary carbocation. However, since we have a tertiary carbon over here, it can lend one of its hydrogens that is attached to it through a hydride shift. And so after that, we end up getting a tertiary carbocation. And through that tertiary carbocation, we can attach methanol over here, and which is basically CH3OH. And so it will attach over here. The hydrogen will be lost as it becomes acidic, and we get this product, which is OCH3 right there. And that is our final product. Now, what about this next example? Well, we have a cyclohexane and we have a methyl that's anti to the bromine, but we have silver nitrate, so we know right away that bromine is going to leave on its own and form a carbocation on this secondary carbon. And so we have our carbocation right here. We have our methyl that's still down there. And then we know that a secondary carbocation can become more stable if a hydride shift happens from the tertiary carbon next to it. And so it can move here, and then it can move here, and then we can get a tertiary carbocation, which would be planar, so we would not say that it's going down, and we'd have this right here. And then our methanol can come and attack it, and once it does, we get this molecule right here. Now we won't show the stereochemistry of this because our methanol can come from either side, either from above this molecule or below, so we can get either stereoisomer. So I'm just not going to show our stereochemistry for this. Now for this third one, over here we have silver nitrate again. So we're going to get another carbocation right there. So we have our benzene ring, we have our carbons, we have our carbocation right here. Now here's the thing, we have two possible hydride shifts. We have this tertiary carbon right here. Let me label them. So we have our tertiary carbon right here that can donate a hydrogen, and we'd get a tertiary carbocation. Or we have this secondary allylic carbon. If it donates a hydrogen, we'll get a secondary allylic carbocation. Now, which is more stable, an allylic carbocation or a tertiary? Well, it's the allylic one. And so the hydrogen from the allylic one is going to move and do a hydride shift, and so we get this carbocation right here. We have our benzene ring, and we have our tertiary carbon. And my bad, that was a benzylic hydrogen, not an allylic one, but it's the same thing. Essentially, it's just resonance stabilization. And so we have our carbocation right here, and the new hydrogen has moved to this carbon. And so water will come and attack that, and so we'll get a benzene ring. We have our carbon that has our new water group, which lost a hydrogen, and we have this final product. Now what about this next example? We have a bromine, and we have a quaternary carbon right next to it, and it's reacted with methanol. So methanol is a weak nucleophile and weak base, and so you can't do SN2 or E2, so we're going to have SN1. And so bromine will have to leave on its own, and we get this cyclohexane right here, with the bottom still going up, this quaternary carbon right here, and we have our carbocation right there. And so methanol can attack this. However, we notice that this quaternary carbon can do something called a methyl shift. And so from this methyl shift, we will end up having this intermediate right here. This carbon on the bottom has not changed whatsoever because the rest of the molecule stays the same. This carbon right here now is the carbocation, and our methyl group has moved to this carbon right here. And so now methanol will attack this tertiary carbocation, which is more stable than a secondary, and your final product is this, where we have our group going up on the bottom carbon. We have our methyl group right here, another methyl group right here, and our methanol. Now I'm not showing stereochemistry simply because we have multiple stereoisomers with Sn1 mechanisms. Now in this next one over here, we have a secondary carbon right here. Now with water and heat, we can't do SN2 or E2, so we can only do SN1 in this situation. And we can actually do E1, but we'll get into that later. So bromine is going to leave on its own, and we get this stereo, or this intermediate right here. We have a carbocation on this carbon. Now we have two possible methyl shifts. We have on this carbon, we can donate this methyl group right here, and on this carbon we can donate this methyl group right here. If we donate the one on the left, we will end up getting a tertiary allylic. So this one will be allylic. The previous one was a benzylic. So this one is a tertiary allylic. And this one, if we donate it over here, we will end up getting just purely a tertiary carbocation. So a tertiary allylic is more stable than a tertiary carbocation. So we're going to do a methyl shift with this carbon right here. And so our next intermediate will look something like this, where we have our double bond, we have our carbon group over here, another carbon group, and the methyl shift methyl that's moved. We still have our quaternary carbon on the edge. Our carbocation is right here. And now water will come and attack it. And so we get our final product, which looks like this. We have our methyl, our OH group. We have our methyl that's shifted from before, and our quaternary carbon. And that is that. Now this last one, this one's special. We notice that we have a strong nucleophile. Not a weak one like water, but a strong one. Sulfur with a negative charge. And we have this bromine, which is on a secondary carbon. Now, seeing this, we would say, oh, this is an Sn2 mechanism. But notice that the neighbor is a quaternary carbon. It has 4 carbon bonds. And the fact that we have a quaternary neighbor makes it impossible for Sn2 mechanism to happen. And you would say, well, maybe we can do an E2 mechanism since this is hindered. Well, sulfur with a negative charge is not a strong base whatsoever. It's still a weak base. And so we're going to go through the Sn1 mechanism. Remember that the Sn1 mechanism purely is based off of the substrate. The nucleophile almost has no effect as long as the substrate is purely hindered. And so bromine is going to have to leave on its own. And so we have this cyclohexane right here, which has the ethyl group going up over here and the methyl going down. And we have our carbocation. Now, a neat little trick to this is to notice that we can't move the ethyl group. We can do methyl shifts, but not ethyl shifts. We can't move 2 carbon groups at one time. And so only the methyl group is going to move to this carbon in order to make the carbocation more stable on a tertiary carbon. And so we're going to move this, and we're going to get this next intermediate right here, where we have now a methyl over here. We have our ethyl here. We're not showing stereochemistry anymore. We have a carbocation intermediate, and now the sulfur with a negative charge is going to come and attack this, and we get this final product where we have our cyclohexane, we have our methyl group, and we have our ethyl group and our sulfur with its CH3 over there. And that is our final product, and the stereochemistry is not being shown. So, just to reiterate what we just did, we had our basic hydride shift, so I'm just going to label that with an H. We have our basic hydride shift, and then another hydride shift, but on a cyclohexane. Here we had another hydride. We have 2 possible hydride shifts, so 2 possible hydride shifts, and then we chose the one that was more stable, which was the benzylic group right here, because if we move this hydrogen, we'll end up getting a benzylic carbocation. Here we just had our regular methyl shift. Here we had 2 possible methyl shifts, and we chose the one that would be more stable in the end, which was the one that would produce a allylic carbocation. On this last one, we noticed that we can't do ethyl shifts. So we can't do ethyl shifts, only methyl shifts. And so that was an Sn1 mechanism.